Alright, this video we are going to cover section 5.2. Applications of exponential functions. Previous video we understood the basic concept of exponential function. We learned the graphs features of the function. We also the last example is how do we solve elementary exponential equations. In this section, we're going to have 3 examples. Those 3 examples are applications of exponential functions. Example 1. Do you remember in previous video, we divide exponential functions into 2 categories. The first category, exponential functions have the base bigger than 1. If the base of the exponential function is bigger than 1, then the exponential function is increasing. So for increasing exponential function, we have a special name for it. We call that exponential growth. Let me write it down. Exponential growth. It is pretty common in real life, actually. And if the base of the exponential function is between 0 and 1, we have learned that that kind of exponential function is decreasing, right? And we call that type of exponential function, the decreasing one, exponential decay. Okay? Exponential growth, exponential decay. So we have 3 examples in this section. The first one is exponential growth. Second example is about exponential decay. And the third example is a compound interest. Compound interest is a very important concept in real life situation. It is belong to exponential growth. So basically, we have 2 growth, 1 decay. Let's get started. Example 1. The number of fruits flies in an experimental population after t hours is given by Q of t equals 20. Do you want me to copy this again? Or do you think you can just look at the notes? So let me write it down. The number of fruit flies in an experimental population after t hours is given by this function. Q of t equals 20 times e to the power of 0.03 t. T here is non-negative. T here is time. Time is never negative. We understand that, right? Look at Q of t. Independent variable t. Dependent variable q. T represents time. Q represents the population of the fruit flies. So you know the fruit flies are producing themselves, right? They have more and more over time. So the amount of or the population of the fruit flies depends on the time. Does that make sense? All right, we need to complete the following 2 parts. Part A, how large is the population? Oops, what happened? I think I pushed something. How large is the population? After 72 hours. Part B. Find the initial number. Of fruit flies in the population. Alright, finally, let's see, how do we complete the two parts? Part A. How large is the population? So we are looking for Q. After 72 hours. So we are looking for the Q value corresponding to T equals 72. Isn't that obvious? So we are looking for Q of 72. So part A, basically we are given the input, the value of the independent variable T. Okay, yeah, so part A, we are given the value of T equals 72. We are looking for the corresponding Q value, the corresponding population. So that is 20 E. We know what is E, right? It's a constant irrational number. 0.03. Plug in T equals 72. You guys should have a calculator, graphing calculator. Where's my graphing calculator? So try to use your graphing calculator to evaluate. And since I do not have a graphing calculator emulator in my Surface, I'm gonna skip this part. All right? Yeah, I believe you can figure out that. It's pretty simple. It's about equal to 172. After 72 hours, the population of the fruit flies is about 172. Simple. You just enter 20, and then there's a function in the calculator, e to the x, and the exponent is 0.03 times 72. Part B, find the initial number of fruit flies. So are we looking for time or are we looking for the population? Yes, we are looking for population. Population corresponds to time equals what? How do you understand initial? Initial means t equals 0, right? Yeah. So part B, actually, we are looking for q sub 0. As the input equals 0, what's the corresponding output? Simple. Same thing. Let me restart it. Part B, q sub 0. 20 e to the power of 0.03 times t equals 0. The power of 0 equals 1. Initially, we have 20 fruit flies. So you can see 20 in the function. This is the function, right? This is the exponential function. The coefficient of the exponential function, actually, that's the initial value of the population. This is a pretty simple, straightforward. Example 2. Is an exponential decay problem. Bill has come upon a 37-gram sample of iodine 131. He isolates the sample and waits for 2 weeks. After this time period, only 11 grams of iodine. What's the half-life of this isotope? What is the half-life of the isotope? What's the goal? The goal is very obvious in the last sentence. Half-life of the substance. How do we understand half-life? Be aware, this is an exponential decay. Okay, so the behavior of the grams or the weight of the isotope is decreasing in this pattern. You can see in the beginning, it is decreasing very fast, right? Of course, this is not exactly the graph of this function, but the behavior of the decreasing is like that. In the beginning, it's decreased very fast, and later, it is decreasing very slow, very slow, and very slow. So how do we define half-life of the substance? Half-life is the time it takes for the isotope to reduce half of its weight. Okay? Half of its weight. Let's say initially the isotope is 37 grams. Then half-life is going to be the time it takes for the 37 grams to reduce to half of it. That's going to be 18.5 grams. Is that clear? Half-life of a substance, which is exponentially decreasing. Half-life of the substance is the time it takes to reduce half of its weight. Okay, so how do we find the half-life though? Firstly, we need to know, since this is an exponential decay problem, we have the function q of t equals q sub 0 times a to the power of t. And q sub 0 must be 37. Remember the initial value? In previous example, the coefficient of the exponential function is the initial value of the population, or the weight. So we have the function q of t equals 37 times a to the power of t. We have an unknown in this function, a, the base a. We do not know the value of a, so we have to figure on our own. Let's see what kind of information do we have. It tells us after 2 weeks, that is 14 days, right? Yeah, let's try here, t is in days, that is 14 days. Since after 14 days, if we plug in t equals 14, the substance remains 11 grams. Do you see here we have this equation? Yeah, this equation only has unknown a. Yeah, we are able to solve a. Divide both sides by 37. We have a to the 14 power equals 11 over 37. And then we are going to raise both sides to the power of 1 over 14. That is kind of like tricky, right? Yeah. Then 14 times 1 over 14 equals 1. We have a by itself on the left. And then on the right hand side, we have 11 over 17 to the power of 1 over 14. Yeah, by the information that we are given, we found the base for the function. The number here must be between 0 and 1 because we are constructing an exponential decay function. All right, so once we have the value of a, we are ready to find the half-life. Let me write the formula, the function again. Q equals Q sub 0 times a to the power of t. We are looking for t, right? This time we are looking for t such that after a period of time, after the t that we are looking for, the population, here is the grams of the substance, becomes half of the initial value. Do you see what happened here? So we know Q sub 0 equals 37, but we don't actually use the value here. We do need it earlier. Sorry, it's 37, not the 17. 37. 11 over 37. Okay? So we are looking for the time t such that after that period of time, the population becomes half of it. Yeah, that's how do we set up this equation. And the Q sub 0 are cancelled out. We have half equals a to the power of t. And we are going to apply natural logarithm. Yeah, this is a kind of like a challenging this part. Okay, then we would have ln half on the left, and we would have t times ln a. Do you see I applied the power rule? I moved the exponent t in front. That is a power rule. We actually learned the power rule later. We're not, but you took the algebra 1, you shouldn't know the power rule here. I can write the formula here. log with base b, x to the power r. You are able to move the exponent on the shoulder of x in front to be the coefficient of the logarithmic function. If you have trouble to understand this point, stop here, and after we finish 5.3 and 5.4, go back and look at this part. Is that okay? And let's continue. So t actually equals ln half over ln a. And a, we have the value already, okay? So we are not going to spend time on that. I can tell you the result is about 8 days, or you can figure out on your own. Through this problem, I want you to understand what is half-life. Exponential decay is different from linear decreasing. Okay? Exponential decay decreasing very fast in the beginning, but slow down later. I have decreases for this day. I have questions in this day quiz asking about half-life. So just think about this example. All right, we have one more example. Example 3. Compound interest. Okay, so in Algebra 2, you have learned the compound interest. You must, or you should, know the two formulas. The first formula, A equals P times 1 plus R over N to the power of N times T. This is the formula for the accumulated balance. If the interest is compounded N times a year, N here is the number of times that the interest is compounded in a year. And T here is time in year. So if you keep your money in an account for 18 months, value of T is not 18, okay? Value of T is 1.5. Yeah, try to figure that. Another formula, A equals PE to the power of RT. That's the formula for the accumulated balance if the interest is compounded continuously. Okay? We know what is E. P here is the principal, your original deposit. R here is APR. Okay? So in our problem, Melissa has recently inherited 15,000 that she wants to deposit into a savings account for 10 years. She has determined that her two best bets are an account that compounds annually. So here I'm going to make a table actually. Two options, right? Compound annually. The first one is compound annually. So n equals 1. And R equals, what is R? 3.95%. That's APR. And another account that compounds continuously. APR is, all right, so 5.1 and 5.2, they are actually is a day, I would say day 19. Yeah, work on your day quiz. Email me if you have any questions. Thank you for watching.